Howdy, I'm Miranda Lobermeyer and I'm a rising junior at St. Norbert College in Wisconsin. This summer I'm working in Dr. Blumel's research group as a part of the Sustainable Chemistry Research Experience for Undergraduates program at Texas A&M University. The research in Dr. Blumel's group fits mainly into the topic of catalysis, which is green chemistry principle number 9. Green chemistry as a whole describes the ways chemistry can be done more efficiently while also being environmentally conscious. With catalysis, this is done in 3 main ways. 1. Having high atom economy. 2. Minimizing the creation of byproducts. And 3. Lowering the activation energy of a reaction. Starting with atom economy, the ultimate goal is to have 100% of the reactants, or the starting materials, fully transform into the desired product by the end of the reaction. Atom economy is calculated using this equation. For example, the atom economy of a Diels-Alder reaction, which led to a Nobel Prize in Chemistry in 1950, is 100%, meaning that all of the materials we started with turned into desired products by the end of the reaction. Minimizing the creation of byproducts also fits in with atom economy because a lower number and amount of byproducts means a higher atom economy overall. Regarding energy, catalysts lower the activation energy needed to complete a reaction. Think of how a spatula is used in baking. The spatula is added in and used to mix together the ingredients and ultimately get the batter ready for the next step. After baking, the spatula is washed and put away, not having changed in the baking process. Now compare this to a catalyst. It is added in to move a reaction along, removed after its use, and is seemingly unchanged in the process. Catalysts may sound like an ideal solution, but they come with a slight catch. Most catalysts are expensive. In addition, homogeneous catalysts are difficult or impossible to separate from reaction mixtures without destroying it or the product in the process. One possible solution for this dilemma is to immobilize catalysts onto an insoluble support. These immobilized catalysts are much easier to remove from a reaction mixture, which also means that the catalyst can be recycled a number of times. Another win for green chemistry! Both solution NMR and solid-state NMR can be used to analyze the chemical structure of a sample. NMR stands for nuclear magnetic resonance and is very similar technology to a traditional MRI, in that the object is observed with the use of a large magnet and radio waves. Think of an NMR like an MRI, except instead of the machine moving around the person for an MRI, the sample itself spins inside the NMR machine. In solid-state NMR, the solid sample is packed into a rotor, which is made of zirconia and can be spun at speeds up to 70 kHz at Texas A&M's instrument, and greater than 150 kHz at other places, which equates to around 4,500,000 revolutions per minute. Phosphines coordinate to most transition metals and can aid in the creation of recyclable systems with palladium catalysts. Palladium catalysts can form carbon-carbon bonds under mild reaction conditions. Because of this, palladium catalysts are being used more frequently. Limited characterization techniques are available for surfaces of amorphous materials such as oil, foam, and silica. We are currently working on creating a methylsilyl tripodal phosphine ligand. This tripod is now a powder in the solid state as opposed to a viscous oil. It's no longer water sensitive, it's easier to crystallize, and the workup steps are already optimized to make this molecule. The crystals created from this tripod could then be investigated using X-ray diffraction, which could help immensely in the characterization process of the substance. Overall, catalysis renders or makes many chemical reactions more effective and more sustainable. Catalysis reduces the energy and resources necessary for a successful reaction while creating a limited amount of byproducts in the process. Thanks for watching!